Right now, the moon is hanging in the sky above half the world, and no one on Earth has ever seen its other side with their own eyes. Not once in all of human history. Not until 4 days ago, on April 6, 2026, 4 astronauts aboard NASA's Orion spacecraft swung around the lunar far side and became the first human beings to see it directly. Not in a photograph, not on a screen. Through 5 windows, with their own eyes in real time, at a distance of 4,066 miles above the surface. They reported what they saw, and what they described was not what anyone expected. The terrain was strange. The craters were enormous and bright in a way that photographs had not prepared them for. The mountains were sharper than anticipated, catching light at angles that gave the far side a different quality of texture. One astronaut compared smaller impact craters to a lampshade with tiny pinprick holes, each one glowing against a background of ancient, undisturbed highland terrain. That is interesting on its own. But it is not the reason scientists are paying close attention right now. The reason scientists are paying close attention is this. Everything Artemis II just confirmed about the lunar far side, every observation the crew relayed, every photograph now being processed, is landing on top of a stack of evidence that has been quietly building for 2 years. Evidence that points towards something deeply strange about the moon itself. Not at the surface, deeper. At the level of its interior, its chemistry, its thermal history, its magnetic field, and its relationship to the early Earth. And the implications of what that evidence suggests are the kind of thing that makes planetary scientists speak carefully in published papers, using language like reshaping our understanding, an unresolved mechanism, and the mystery of lunar asymmetry remains one of the key unsolved problems in planetary science. This is not speculation. This is what the data says. If this is the kind of investigation that interests you, subscribe now. The investigation begins here. You are standing on a planet whose moon is, in a precise and measurable sense, 2 completely different objects depending on which side you look at. The side facing you is familiar. Dark plains, ancient lava seas, relatively smooth terrain. 12 humans have walked on it. Hundreds of kilograms of its rocks sit in laboratories. We have been studying this side for 60 years and calling it lunar science. The side that never faces you is something else entirely. Heavily cratered, mountainous, brighter, thicker crusted, geochemically stripped, colder in its interior, drier in its mantle, and no one, not one human being, had seen it with their own eyes until this week. That asymmetry is the mystery, and we are now, for the first time in history, getting the tools to understand it. Let us start with what the Artemis II crew actually saw and what they felt, because the feeling matters here as much as the measurement. On April 6th at 7:02 in the evening Eastern Time, the Orion spacecraft reached its closest approach to the moon, 4,066 miles above the surface. That sounds like a great distance, and in most contexts it would be. But in the context of the moon, in the context of what the crew was trying to do, it is intimate. The Apollo astronauts orbited 60 miles up. Artemis II was not orbiting. It was on a free return trajectory, a precisely calculated arc that would take the spacecraft around the far side and use the moon's gravity to slingshot it back toward Earth. The crew had no engine burn to change their path. Physics was driving now. At 7:02 they crossed behind the moon. Radio contact with Earth dropped to nothing. Mission control in Houston went silent. Not because anything went wrong, but because the moon itself was between them and every radio transmitter on Earth. The crew of Artemis II were more alone than any human beings had ever been. For approximately an hour, they were unreachable. No communication, no telemetry, nothing. In that hour, they looked out the windows. Victor Glover described the Terminator line, the boundary between the lit side of the moon and the dark side, as jagged. Not the smooth curving line you see in photographs, The far side mountains are higher than anything on the near side. The moon's tallest peaks, measured from base to summit, are on the far side. They reach 7,000 meters. That is higher than Mont Blanc. When sunlight catches those peaks at a low angle, the shadows they cast are long and sharp, and the terminator becomes something violent looking, something that photographs flatten, but a human eye perceives in 3 dimensions. Glover's description of it carries weight precisely because he was not looking at a photograph. He was looking at the real thing through a real window from a position in space that no human had ever occupied. Christina Koch looked at smaller, more recent impact craters, the bright fresh scars left by impacts over the last few 100 million years, and described them as brighter than expected, more vivid. She said it looked like a lampshade with tiny pinprick holes, each bright impact, surrounded by a halo of excavated material that caught the light. This observation is scientifically relevant. Those bright halos are not just visual phenomena, they are excavated subsurface material thrown to the surface by the impact event. Each bright ring around a crater is a sample of what lies beneath the lunar regolith at that point. Near the South Pole, near the rim of the largest impact scar in the solar system, those windows into the subsurface may contain some of the most important materials in lunar science. Commander Reed Wiseman described the overall experience as overwhelming in a way photographs had not prepared him for. There is something about seeing a geological object of this scale with human eyes that does not translate through a camera. The depth of field, the way light falls across uneven terrain, the parallax as the spacecraft moves and the landscape shifts. He had trained for years for this mission. He had studied maps and photographs and orbital imagery, and the real thing was still more than he expected. The crew also saw the South Pole Aitken Basin. From their altitude, moving at several miles per second across the lunar sky, they could perceive its scale in a way that orbital photography does not fully convey. It is 2,500 kilometers across. To give that number room, 2,500 kilometers is roughly the distance from London to Cairo. It is the distance from New York to Denver. It is a wound in the moon's surface so vast that if you stood at the center of it and looked toward the rim, the horizon itself would curve slightly downward. You would be at the bottom of a depression so enormous that its edges are beyond any natural visual horizon. That basin is where the real story begins. And the story starts not with the Artemis mission, but with an event 4.25 billion years ago that changed the moon in ways we are still measuring. The South Pole Aitken Basin is not just the largest impact crater on the moon. It is one of the largest confirmed impact structures in the entire solar system. It is between 6 and 8 kilometers deep. The lowest point on the moon is inside it, sitting roughly 9 kilometers below the surrounding highland terrain. The rim mountains rise to 8,500 meters above the basin floor. When the object that formed this basin hit the moon, the energy released was equivalent to approximately 1 trillion atomic bombs. Not one, not 1,000, 1 trillion. In a fraction of a second, an area the size of Western Europe was excavated to a depth that would swallow most mountain ranges. The impactor punched through the crust and into the lunar mantle. It did not just leave a crater, it changed the moon. That impact happened 4.25 billion years ago. We know this now with precision, because of a mission that quietly changed everything we understand about the moon's far side, 18 months before Artemis II launched. In June of 2024, a Chinese spacecraft called Chang'e 6 landed in the Apollo Basin, a smaller crater sitting inside the South Pole Aitken Basin on the far side of the moon. It scooped up 1,935 grams of lunar material from the surface. It sealed that material into a return capsule. It launched from the lunar surface, rendezvoused with an orbiter in lunar orbit, transferred the sample container, and sent it back to Earth, where it landed safely in the deserts of Inner Mongolia on June 25, 2024. That was the first time in human history that a sample had been returned from the lunar far side. Let that sit for a moment. In 65 years of robotic and human lunar exploration, every rock we had ever brought back from the moon came from the near side, the side we can see. We had been reading one page of a 2-page book and calling it the complete text. Every model of lunar formation, every theory of lunar thermal evolution, every calculation about the moon's interior chemistry was built on samples from a single hemisphere. The analysis of the Chang'e 6 far-side samples has been published across multiple papers in Nature, in Science, and in other peer-reviewed journals. What those papers reveal is strange in a way that demands attention, not because it's surprising that the two sides differ, but because the depth and nature of the difference is more profound than any existing model had cleanly predicted. To understand why, you need to understand what scientists expected to find and what they actually found, and where the gap between those two things is. The moon's two faces have been known to be different since 1959, when the Soviet Luna 3 spacecraft photographed the far side for the first time. Those images were blurry and low resolution, but they showed something unmistakable. There were no dark plains, no Maria. The terrain was bright and heavily cratered from edge to edge. Where the near side was punctuated by dark volcanic seas, covering about 31% of the surface, the far side was a uniform highland landscape covered in craters and covering volcanic plains in only about 1% of its area. Later missions confirmed and deepened the asymmetry. The Grail mission in 2012 mapped the moon's gravitational field in extraordinary detail using twin spacecraft that measured the variations in their separation to a precision of a few micrometers. What those measurements revealed about the moon's interior structure produced one of the clearest pictures of planetary asymmetry in the solar system. The crust on the near side of the moon is, on average, between 30 and 40 kilometers thick. The crust on the far side is between 50 and 60 kilometers thick, and in some places significantly more than that. That is not a small difference. That is approaching double in the most extreme regions, and the implications of that difference go far beyond surface appearance. The crust determines how easily magma can push through from the mantle below. A thin crust is permeable to volcanic activity. A thick crust suppresses it. On the near side, the ancient crust was thin enough that hot mantle material could force its way upward, flood the low-lying basins, and cool into the dark volcanic plains we see today. On the far side, the crust was thick. The magma could not break through. The surface stayed geologically ancient, piled deep with impact craters, untouched by the volcanic resurfacing that remade the near side. That much was known and modelled, if not fully explained, before Chang'e 6. What was less understood was why the crust thicknesses were different in the first place. The leading model involves the early history of the moon's formation. When the moon coalesced from the debris of the collision between the early Earth and a Mars-sized body called Theia, approximately 4.5 billion years ago, the entire moon was molten. It was a global magma ocean, a sphere of liquid rock cooling over millions of years. As it cooled, lighter minerals floated upward and began forming the crust. Heavier minerals sank toward the center, but Earth was there throughout this process, and Earth was closer then, much closer, roughly 15 times closer than it is today. The moon had been captured by Earth's gravity and was already tidally locked, meaning the same side always faced Earth, the side we call the near side. Earth in those early years was itself a furnace, radiating enormous heat from the collision that created the moon and from its own radioactive decay. The near side of the moon, permanently facing this radiating furnace, experienced significantly more heat than the far side. The near side stayed warmer longer. The crust-forming minerals on the near side condensed and solidified later than on the far side. The far side cooled faster, forming its crust earlier, and that crust grew thicker. The near side crust formed more slowly and ended up thinner. This is confirmed science. The thermal asymmetry caused by the early Earth's heat is the leading explanation for why the two crusts are different thicknesses. But here is where the mystery deepens, because the crustal thickness difference is only the beginning. The near side does not just have a thinner crust, it has a fundamentally different chemical composition. Deep in that crust and in the mantle beneath it, there is a region on the near side called the Procellarum KREEP terrain. KREEP stands for potassium, rare earth elements, and phosphorus. These are elements that were among the last to solidify when the lunar magma ocean cooled. They are incompatible with the main rock-forming minerals, meaning they do not fit neatly into the crystal structures of olivine or pyroxene. They get excluded, pushed out, concentrated into whatever liquid magma remains. The last bit of the lunar magma ocean to solidify would have been rich in KREEP, and that last bit ended up concentrated on the near side. A map of creep distribution on the Moon looks like a bruise on the near side surface, a region roughly 2,500 kilometers across, centered on the ocean of storms. The rest of the Moon, and in particular the far side, has almost no KREEP signature. The far side is depleted, chemically stripped of the radioactive heat-producing elements that define the near side's thermal character. This matters enormously. Potassium-40 uranium and thorium are all heat-producing elements. Wherever they concentrate, they generate heat as they decay, over hundreds of millions and billions of years. The creep-rich near side has been warmer for longer than the far side. The volcanic activity that kept the near side Maria fresh and flowing as recently as 2 billion years ago was powered, at least partly, by the radioactive heat locked in the near side crust. The far side, depleted of these elements, cooled faster, went volcanically quiet earlier, and stayed cold and ancient. But here is the question that planetary scientists cannot yet fully answer. How did KREEP end up on one side and not the other? The thermal argument explains some of it. If the near side cooled more slowly due to Earth's heat, the last dregs of the magma ocean, the KREEP-rich residue, would have been concentrated there when it finally solidified. But the concentration is sharper and more asymmetric than simple thermal models alone predict. Something else may have been involved. The strongest candidate is the South Pole Aitken impact. Think about what that impact did. An asteroid, possibly 200 kilometers across, struck the far side of the Moon with energy equivalent to 1 trillion atomic bombs. It punched through the far side crust. It excavated material from the lower crust and upper mantle. It melted an enormous region of the lunar surface and interior. It blasted debris across the Moon in asymmetric patterns determined by the angle and direction of the impact. Research published in Nature in October 2025 by a team at the University of Arizona determined, by analysing the shape of the South Pole Aitken Basin in detail and comparing it to other giant impact basins across the solar system, that the impact came from the north, not from the south, as previously assumed. Impact basins formed by oblique strikes narrow in the downrange direction. The SPA basin narrows toward the south. The impactor came from the north. This matters because it changes where the deeply excavated material from the impact should have been scattered. In a northward impact, the bulk of the ejector, the material thrown out of the Moon's interior by the collision, goes southward. And when the researchers mapped the distribution of radioactive thorium around the basin, they found a pattern that matches a northward-coming impactor. The KREEP-rich material, excavated from deep in the Moon's interior by the impact, was scattered toward the south, toward the rim of the basin, toward the terrain where future Artemis astronauts are now planning to land. This may be the mechanism that concentrated radioactive heat-producing elements on the near side. The SPA impact on the far side excavated material from deep in the Moon and blasted it outward in an asymmetric pattern. Over subsequent billions of years, the reheating of the near-side crust and mantle by those radioactive elements drove the volcanic activity that made the near side look the way it does. The cause was on the far side, the effect was on the near side, and the agent was an impact so violent that we are still tracing its consequences 4.25 billion years later. Now let us talk about what Chang'e 6 actually found in those 1,935 grams of far-side material, because the findings went further than confirming the expected depletion. The rocks recovered from inside the South Pole Aitken Basin were volcanic basalts. They had erupted onto the lunar far side, which was already surprising. The far side was supposed to be largely dead. When scientists dated those basalts using radiometric methods, including precise measurements of lead isotope ratios and rare earth element systematics, they found the basalts were 2.8 billion years old. This was confirmed and published. The far side had active volcanism as recently as 2.8 billion years ago. That is later than many models had predicted for far side volcanic activity. And when you combine it with earlier findings that the near side had volcanic activity as recently as 2 billion years ago, the picture that emerges is of two hemispheres that were volcanically active at overlapping times, just at different rates and in different ways. But the chemistry of those basalts is what created the real disruption in existing models. The far side basalts are, in the language of the published research, ultra-depleted. They came from a mantle source region that was geochemically stripped of the incompatible heat-producing elements that dominate the near side. No KREEP, no anomalous concentrations of potassium or rare earths. The mantle that produced these basalts was deeply impoverished, and yet it produced basalts, which means it was hot enough to melt, which means the volcanism on the far side, even 2.8 billion years ago, was not driven by radioactive heat. It was driven by something else. The researchers' leading candidate is that the thin crust at the bottom of the Apollo basin, ground down even further by the overlapping South Pole Aitken impact, allowed pressure release melting of the mantle without requiring as much heat. Where the crust is thin, rock can melt at lower temperatures because the pressure above it is lower. The far side volcanism may have been a local phenomenon enabled by geography rather than a global thermal event. This is not a fully resolved question, it is a complication, another layer in the puzzle. The water story is equally unexpected. The lunar interior was long assumed to be essentially dry. When the moon formed from the debris of the Theia collision, the enormous heat generated should have vaporized and driven off most volatile compounds, including water. For decades, textbooks described the moon as anhydrous, dry throughout. That story began changing around 2008 when sensitive analysis of volcanic glass beads from Apollo samples revealed traces of water locked in the interiors of those glass droplets. The water was not abundant, but it was there. And in the years since, multiple lines of evidence have confirmed that the lunar mantle contains small but real amounts of water. The moon is not dry. It is damp in the way that a rock looks dry to the touch, but contains bound hydroxyl molecules in its crystal structure. What Chang'e 6 revealed is that the far side mantle is significantly drier than the near side mantle. The far side basalt samples, when analysed for water content in their minerals, pointed to a mantle source that contained less water than equivalent near side rocks. This is yet another asymmetry. The near side is warmer, creep-rich, thinner crusted, and wetter in its interior. The far side is colder, creep-depleted, thicker crusted, and drier in its interior. Why would the interior water content be asymmetric? One possibility connects back to the South Pole Aitken impact. The enormous heat generated by a trillion bomb impact would have driven volatile loss from the surrounding region. Water-bearing minerals would have decomposed. The water would have escaped as steam into space. The far side hemisphere, closer to the impact zone, would have experienced more severe volatile loss than the near side. A single catastrophic event might have simultaneously altered the chemistry, temperature, volcanic history, and water budget of the Moon's interior in a pattern that has persisted for 4.25 billion years. But this remains a hypothesis, not a confirmed mechanism. Multiple teams are testing it against the data. The answer is not yet in. And then there is the buried mass under the South Pole Aitken Basin, which is in some ways the strangest part of the story. The Grail mission, which mapped lunar gravity to extraordinary precision, detected a large positive gravity anomaly beneath the floor of the South Pole Aitken Basin, a region where the Moon is denser than it should be, based on the surface composition and topography alone. The anomaly implies a mass of dense material sitting in the lunar mantle beneath the basin floor. That mass is approximately 5 times larger than Hawaii's Big Island. It is pulling the basin floor downward by more than half a mile. Nothing in standard models of lunar formation predicts this. There should not be a concentrated mass of dense material sitting in the mantle beneath the largest impact crater on the Moon. But it is there. It has been measured by multiple independent methods. It is confirmed. The leading hypothesis is that it is the metallic remnant of the impactor itself. The asteroid that carved the South Pole Aitken Basin may have been large enough, and the impact geometry such that a significant portion of its iron-rich core survived the collision and sank into the lunar mantle rather than being dispersed and mixed with the surrounding rock. 4 billion years later, the impactor is still there. A piece of the asteroid that reshaped the Moon is sitting in the Moon's interior, and we can detect it by the way it bends the Moon's gravitational field, if that is what it is. The second hypothesis is that the mass is the result of differentiation within the impact melt sheet. When the asteroid struck and generated a vast pool of molten rock covering the entire SPA region, that melt would have cooled and differentiated over millions of years. Dense titanium-rich oxide minerals may have sunk to the bottom of the melt sheet and accumulated there in a layer that persists today. This is chemically plausible, but it would require a specific set of conditions, and the mass is large enough that this explanation strains the available geochemical models. Neither explanation is ruled out. Neither is confirmed, and the only way to distinguish them is to send instruments into the region and measure the deep interior directly. The lunar magnetic story adds yet another layer of complexity. The Moon today has essentially no global magnetic field. It has no active dynamo generating a protective magnetosphere the way Earth does. The Earth's magnetic field is generated by convection in its liquid iron outer core, a process called the geodynamo. The Moon's core is much smaller, and it has cooled to the point where core convection has ceased or nearly ceased. The dynamo has wound down, but the Moon did have a magnetic field once. Ancient lunar rocks are magnetized. They record the direction and intensity of a field that was active when they cooled from their molten state. The Apollo samples allowed scientists to reconstruct the history of the lunar magnetic field over the last 4 billion years. The story they told was one of gradual decline. A field that was strong early, powered by the active early core, and that faded over billions of years as the core cooled and the dynamo ran down. The Chang'e 6 far-side samples have complicated that story. The magnetic record preserved in the far-side basalt clasts shows an unexpected pattern. Rather than continuing the smooth decline that near-side samples suggested, the far-side record shows evidence of a magnetic field, a rebound around 2.8 billion years ago. The field intensity appears to have increased at that time, rather than decreasing. This is a fluctuation, a departure from the simple narrative of steady decline. A rebounding lunar dynamo implies that something was adding energy to the core, something that reinvigorated convection at a time when the core should have been too cool to generate significant magnetic activity. What that energy source was is not known. Some researchers have proposed that large impact events could have generated mantle overturn, events that briefly reactivated core convection. Others have proposed that the same radioactive heating on the near side that drove volcanic activity could, through complex mantle dynamics, have influenced core behavior. These are speculative mechanisms. They are being tested against the data now. What is confirmed is the observation. The far-side magnetic record shows a more complex history than near-side samples suggested. The Moon's magnetic evolution was not a simple decline. Something happened at 2.8 billion years ago, and it shows up in rocks that spent 2.8 billion years sitting on the floor of the South Pole Aitken Basin, recording whatever field was present when they cooled. All of this, the chemical asymmetry, the thermal asymmetry, the volcanic history, the magnetic fluctuation, the buried mass, the water distribution, comes together in the picture that planetary scientists are currently trying to assemble. And that picture, while not yet complete, is pointing toward a conclusion that has significant implications. The Moon is not just two geologically different hemispheres. The differences between the near side and the far side are so deep, so pervasive, and so interconnected that they almost certainly trace back to a single early event. The most probable candidate for that event is the South Pole Aitken impact, the collision that carved the largest confirmed impact structure in the solar system may have done more than just leave a crater. It may have reorganized the Moon's interior. It may have driven the KREEP elements toward one hemisphere. It may have driven volatile loss from the far side. It may have induced the mantle overturn dynamics that concentrated heat-producing elements on the near side and kept the far side mantle cold and depleted. It may have set in motion a chain of geological consequences that played out over billions of years and that we are still reading in the rocks. If this is correct, then the Moon is not a symmetrical body with two faces that happen to look different. It is a body that was fundamentally restructured by a single catastrophic event 4.25 billion years ago, and everything we observe about it today, near side and far side both, is downstream of that event. This is a large claim. It is not yet proven, but it is what the current data suggests, and the Artemis II mission has just provided the first human-scale confirmation that the far side is as strange and distinctive as the measurements indicated. Let us return to the crew for a moment, because something happened during the flyby that belongs in this story. After crossing behind the Moon and spending an hour in radio blackout, the crew re-established contact with Earth and relayed their observations in real time. For 7 hours during the flyby, they described what they saw. The science team on the ground responded with the names of geological features, confirmed observations, shared data, turned the flyby into a real-time scientific conversation. At one point, mission specialist Jeremy Hansen identified a crater that straddles the boundary between the near side and the far side, a bright spot visible from Earth under the right conditions. He proposed naming it Carol, in honor of Commander Reed Wiseman's wife, Carol Taylor Wiseman, who died in 2020. The proposal was transmitted to Mission Control, heard by the science team, entered into the record. From 4,000 miles above a world that no human had seen from that angle in all of history, a man named a crater for someone who was no longer alive to see it. Lunar science lead Kelsey Young later described the moment as powerful for everyone listening. The Artemis missions are about more than science. They are about the continuation of a project that has been going on since the first human being looked up at the Moon and wondered what it was. And then there was the eclipse. During the flyby, the Moon moved between the spacecraft and the Sun. From behind the Moon, in a region of space where no human had ever been, the crew watched the Sun disappear. The solar disk was blocked by the lunar body, and the corona appeared, the outer atmosphere of the Sun, a thin luminous veil around the darkened disk. Victor Glover described it as a halo. The corona was bright enough to create an almost full ring of light around the dark Moon. The crew used eclipse viewers, standard solar observation equipment, to safely watch the sun reappear on the other side of the lunar disk. During totality, they could see stars that are normally drowned out by the sun. They identified planets. Mars and Venus were visible, Saturn, Mercury, on the other side of the disk. Someone said one of the red points of light looked brighter, redder. Kelsey Young told them, "That is Mars. You are looking at your future." The Artemis program is explicitly a step toward Mars. NASA's stated goal is a crewed Mars landing in the early 2030s. The Moon is both the destination and the proving ground. Everything learned about surviving and working in deep space during the Artemis missions feeds directly into the planning for the first crewed Mars mission. But while the crew was looking at their future, what they were standing above was ancient. The terrain below them was the most ancient surface they had ever seen. The Farside Highlands have not been volcanically resurfaced in billions of years. The crust beneath those craters formed when the solar system was young, when the inner planets were still being assembled, when the rain of debris that would eventually give Earth its water was still ongoing. The rocks in the South Pole Aitken Basin at the bottom of that enormous depression are windows into the first 300 million years of the solar system's existence. They are among the oldest materials anywhere in the inner solar system. When the Artemis II mission lands near the South Pole, and it will land on terrain that the Artemis II crew have now directly observed, the astronauts will be standing on some of those ancient materials. Not just impact mixed surface regolith, but ejecta from the South Pole Aitken impact itself. Material thrown up from the Moon's interior by the Trillion Bomb event 4.25 billion years ago, sitting on the surface, waiting to be picked up, brought back to Earth and analysed. The researchers at the University of Arizona who determined that the SPA impact came from the north predicted, based on their impact trajectory model, that the south rim of the basin should be rich in this deeply excavated material. The planned Artemis landing zone is at the South Pole, at the south end of the basin. The crew of Artemis II have now confirmed that the terrain in that region is as complex and geologically layered as the models suggest. The observations about bright crater halos and the unusual albedo patterns Koch described are consistent with a surface that has been churned by multiple large impacts over billions of years, and that contains materials from different depths and different times. Picking up a rock from that surface and carrying it back to Earth is not a simple act. It is the recovery of evidence from the scene of the most violent event in the Moon's history. It is reading the record of something that happened before our planet had continents, before life had taken hold, before the oceans had fully formed. It is archaeology on a geological timescale. Here is where the investigation stands right now, at the beginning of April 2026, with the Artemis II crew on their way home and the data still being downloaded and processed. We know, confirmed by multiple independent measurements, that the Moon's two hemispheres are fundamentally different. We know the near side is KREEP rich, thin-crusted, volcanically active, for longer, warmer in its mantle, and wetter in its interior. We know the far side is KREEP depleted, thick-crusted, volcanically limited, colder in its mantle, and drier in its interior. We know the South Pole Aitken Basin is the oldest and largest impact structure on the Moon, formed 4.25 billion years ago. We know there is a massive dense object sitting in the lunar mantle beneath that basin, with no fully satisfactory explanation. We know the far side was volcanically active 2.8 billion years ago from a depleted mantle source. We know the lunar magnetic field rebounded rather than declining steadily. We know the SPA impact probably came from the north, distributing radioactive ejecta toward the south and possibly toward the near-side hemisphere. We know the Artemis II crew have directly confirmed the terrain characteristics predicted by these models. All of this is established. Multiple independent teams, published literature, peer-reviewed. This is not speculation. Before we get to what we do not yet know, let us take a moment with something that gets almost no coverage in the popular science discussion of the moon's far side, because it is the kind of detail that only becomes significant when you have enough other pieces in place to understand why it matters. The moon rings, not metaphorically. When the Apollo 12 mission deliberately crashed the lunar module ascent stage into the moon's surface in 1969, seismometers left on the surface recorded something unexpected. The moon vibrated for almost an hour. Seismologists described it as ringing like a bell. The vibrations did not decay quickly, the way they do on Earth. They persisted, reverberating through the lunar interior for many times longer than comparable impacts on Earth would produce. This was the first indication that the lunar interior was fundamentally different from Earth's interior in its physical properties. On Earth, seismic vibrations decay quickly because the interior is wet. Water at depth acts as a damping medium, absorbing seismic energy and dissipating it relatively quickly. The moon's interior, as indicated by those long-ringing seismic events, was dry. Dry rock transmits seismic energy for much longer. The ringing was evidence of dryness, but here is the complication. The near-side interior and the far-side interior are different in ways we do not yet fully understand, precisely because all of our seismic data comes from instruments placed on the near side. The 4 Apollo seismic stations were all on the near side. They recorded moonquakes and impact events and built up a model of the lunar interior that describes the near-side structure in reasonable detail. The far side has never had a seismometer. This matters because seismic waves that pass through the far side, or originate there, are heard only weakly or not at all by near-side instruments. We are, in a sense, deaf to the far side's inner voice. The crustal thickness and mantle structure on the far side are currently inferred from gravity data, from impact topography, from geochemical proxies. We have not measured them directly the way we have measured the near side. The far side seismic suite, a small seismometer package, was delivered to the lunar far side as part of an earlier commercial lander mission. It recorded moonquakes and provided the first ever seismic data from the far side of the moon, though the instrument's operational lifetime was limited. What it revealed in its brief window of operation is that the far side seismic environment is different from what the near side instruments recorded. The types of moonquakes, their frequencies, their depths, their characteristic signatures are not identical between the two hemispheres. The interior of the far side behaves differently under seismic stress than the interior of the near side. This is confirmed. It is not yet understood. There is also the matter of the lunar swirls. Scattered across the moon's surface, mostly on the near side but present on the far side as well, are strange bright markings that look like someone drew on the moon's surface with a luminous paintbrush. They are not craters. They are not volcanic features. They have no topographic relief, meaning they are not ridges or valleys. They are simply regions where the surface material is brighter than the surrounding terrain, arranged in sweeping, sinuous patterns that can stretch for hundreds of kilometers. The most famous of these is Rhina Gamma, a swirl on the near side that has been photographed from Earth for centuries. Astronomers noticed it long before spacecraft visited the moon. It looks like a glowing comma, a bright central core with sweeping tails. It is beautiful and it is mysterious, and for a very long time, no one had any idea what caused it. The answer, confirmed by orbital measurements, is magnetic. The lunar swirls are located at the centers of magnetic anomalies, regions where the lunar crust is locally magnetized in a way that deflects the solar wind, the stream of charged particles flowing outward from the sun. On Earth, the magnetosphere deflects the solar wind at the planetary scale. On the moon, with no global field, the solar wind normally reaches the surface directly. It bombards the regolith, alters the surface chemistry, and darkens the soil over time through a process called space weathering. But at the swirls, there is a local magnetic field. The solar wind is partially deflected. The soil beneath the magnetic anomaly is shielded from space weathering and stays brighter longer. The swirling pattern in the bright material mirrors the structure of the underlying magnetic field, which itself has a complex looping geometry. The question is where the magnetism comes from. The Moon has no active dynamo. There is no mechanism currently generating the field. The magnetism must be a relic, something frozen into the rock when it cooled in the presence of a field that no longer exists. The rocks in the swirl regions are magnetized ancient material, but how did such localized, intense magnetism get into those specific regions? One theory involves the antipodal focusing of impact shockwaves. When a very large asteroid strikes the Moon, the shockwave generated by the impact travels outward through the lunar interior. When two such shockwaves, traveling through opposite sides of the Moon, meet at the point directly opposite the impact, they interfere constructively, generating intense local pressures. That intense pressure event at the antipode can magnetize the surrounding rocks if a global magnetic field was present at the time, imprinting the field direction and intensity into the mineral grains. Under this model, the large impact craters on the near side, such as the Imbrium Basin, should have corresponding magnetic anomalies on the far side at their antipodal points. And indeed, some magnetic anomalies on the far side do appear to cluster near the antipodal positions of large near-side impact basins. The pattern is not perfect. There are anomalies that do not fit this model, but the correlation is real enough to be significant. Reiner Gamma is the antipode of no specific large impact basin. Its origin remains contested. It may involve a cometary impact, which would produce a different kind of magnetic imprinting than an asteroidal impact. It may involve an intrinsic concentration of magnetic minerals in the underlying crust. The Lunar Vertex mission, designed specifically to land at Reiner Gamma and make in situ measurements of the magnetic field structure, is intended to resolve this. It has not yet flown. What the swirls tell us, taken together with everything else, is that the Moon's interior is magnetically complex in ways that our models have not fully captured. The magnetic history of the Moon, the rise and fall and apparent rebound of the dynamo, the localized anomalies, the antipodal focusing, all of these are connected to the thermal and chemical evolution of the interior in ways that are only beginning to become clear. And then there is the question of water ice in the permanently shadowed craters, which is directly relevant to what will happen when humans eventually stand on the lunar South Pole. The permanently shadowed regions near the poles are places where sunlight has never reached in billions of years. The geometry of the lunar terrain, the deep craters whose floors lie permanently below the horizon from the sun's perspective, creates cold traps. Temperatures in these craters drop to around -180 degrees Celsius. At those temperatures, volatile compounds including water can survive essentially indefinitely. Multiple instruments on multiple missions have confirmed the presence of water ice in these permanently shadowed regions. The LCROSS mission in 2009 deliberately crashed a rocket stage into Cabeus crater near the South Pole and confirmed water in the resulting ejector plume. The Lunar Reconnaissance Orbiter has mapped the distribution of hydrogen across the lunar surface and found elevated hydrogen concentrations near the poles, consistent with water ice. The Chandrayaan-1 mission detected hydroxyl signatures using its infrared instruments. This is established. Water ice is on the Moon, at the poles, in the permanently shadowed craters, but the distribution of that water is strange. It does not match simple models that predict it should fill every permanently shadowed crater uniformly. Instead, concentrations are patchy, varying dramatically between adjacent craters that appear to have similar thermal conditions. Some craters have abundant ice. Others, nearly identical in size and depth and shadow coverage, have almost none. The Chang'e 6 finding that the far side mantle is drier than the near side mantle adds a layer to this. If the moon's interior is geochemically asymmetric with respect to water, then the volatile history of the two hemispheres might be different in ways that affect the surface water distribution. The near side might have been episodically outgassing water from its warmer, wetter mantle through volcanic activity over the last 2 billion years, adding to the polar ice deposits. The far side, with its drier interior, might have contributed less water through outgassing, but comets and asteroids also deliver water to the moon. The impactor record preserved in the South Pole Aitken Basin includes evidence of multiple large impacts over billions of years. Some of those impactors carried water. The distribution of their impact debris and the water contained within it would have been asymmetric depending on the geometry of the impacts. We do not yet have a satisfying integrated model for where the polar water came from, how much of it there is, and how it is distributed between the near and far sides of the moon. These questions will be partially answered when the Artemis and Chang'e missions make direct measurements at the South Pole, but the answers will require integration with what we know about the interior chemistry, the volcanic history, the impactor record, and the thermal evolution of both hemispheres. It is not one mystery, it is several connected mysteries that share a common root. The common root may be the moon's formation itself. The giant impact hypothesis, the idea that the moon formed from the debris of the collision between the early Earth and Theia, is the leading model for lunar origin. It is supported by multiple lines of evidence: the moon's bulk composition, the isotopic similarities between Earth and lunar rocks, the angular momentum of the Earth-Moon system, the physical properties of the moon's interior. It has been the consensus view since the 1980s, but variants of the model are still being argued about. How large was Theia? What was its composition? At what angle did it strike? How much material came from Earth, and how much from Theia? Was the impact a single event or part of a sequence? These details matter because they determine what the moon's initial composition was, how the magma ocean formed and cooled, and what the initial distribution of elements was before any subsequent events modified it. Some researchers have proposed that the moon's asymmetry is partly primordial, that the collision geometry itself, the direction and angle of the Theia impact, created an initial difference in how the two hemispheres of the newly formed moon crystallized from the magma ocean. Others argue that the asymmetry is entirely the result of subsequent events, particularly the South Pole Aitken impact, acting on a moon that was initially more symmetric. The samples from Chang'e 6 and the samples that Artemis II will bring back from the South Pole will help distinguish between these possibilities. The age distribution of different rock types, the isotopic signatures frozen in ancient minerals, the trace element chemistry that varies between near-side and far-side rocks. All of these are pieces of evidence that can be used to reconstruct the sequence of events that produced the moon we see today. Let us also reckon with something that tends to get lost in the scientific detail: why the far side being hidden matters to us in a way that is not purely scientific. The moon has been above us for all of human history. Every civilization that has ever existed has seen it. Every calendar system has organized itself around its cycles. Every poet who has ever written about the night sky has looked at it. It is so familiar, so constant, so present, that it has almost become invisible through familiarity. We look at it without seeing it. We take for granted that it is what we understand, and the far side has been the edge of that understanding for as long as understanding has existed. Not just scientifically, psychologically. It is the thing behind the familiar face, the side we cannot see. Dark side is a phrase that entered the culture long before any album used it. The far side is where we put the things we could not verify. None of those invented things are there. What is there is stranger than any mythology, in the way that confirmed reality is almost always stranger than invented mystery. What is there is a surface that has been heavily bombarded for 4.5 billion years, that has never been softened by volcanic resurfacing the way the near side has, that preserves a record of the solar system's violent infancy in a form that the near side no longer shows. What is there is the rim of a wound from a trillion bomb impact that may have determined the chemistry of both hemispheres. What is there is a crust 60 kilometers thick in places, a mantle cold enough to have suppressed volcanic activity for most of the moon's history, a surface that is brighter than the near side because it has not been darkened by billions of years of lava floods. What is there is the oldest landscape in the inner solar system. Ancient in the specific sense that the rocks on the far side highlands formed before life existed on Earth, before Earth had continents, before the oceans were full, before the sun had converted even a small fraction of its hydrogen to helium. Those rocks formed 4.5 billion years ago, when the moon was newly coalesced, still cooling from its molten state. They have sat on the far side since then, accumulating impact craters, unvolcanized, unaltered. When Artemis II astronauts eventually pick up rocks from the South Polar region, they will be handling objects that formed when the solar system was perhaps 100 million years old. The entire subsequent history of Earth, 4.4 billion years, of continental formation, ocean chemistry, evolution, the rise of Homo sapiens, civilization, writing, science, all of it fits between the formation of those rocks and the moment a gloved hand lifts them from the regolith. The Earthsat photograph is the image this mission will be remembered for, at least by the public. Earth dipping below the far side horizon, the planet going dark, home disappearing. It is the other side of Earthrise. In 1968, the Earthrise photograph taken by the Apollo 8 crew showed Earth emerging above the near-side lunar horizon and changed how many people understood their relationship to the planet. Earthsat is the same image from the other direction. Not the planet appearing, the planet going away. And in that disappearance, a question that is both scientific and human. What is on the other side of the thing that hides our world from view? The answer, confirmed this week by the first human beings to see it, is one of the oldest and strangest landscapes in the solar system, sitting above a geological interior whose mysteries are only now beginning to yield to measurement, pointing back toward an event 4.25 billion years ago that may have determined the nature of both faces of the moon and left a record in the rocks that we are only now developing the tools to read. What is perhaps most striking about where lunar science stands right now is how much we still do not know about an object we can see with our naked eyes on any clear night. The moon is 384,400 kilometers away. The distance to the nearest star is about 40 trillion kilometers. In the context of the universe, the moon is so close as to be almost touching. We have sent 108 robotic missions to it. 12 humans have walked on it. We have retrieved 382 kilograms of its rocks. We have mapped its gravity field, its magnetic field, its topography, its chemical composition from orbit, with instruments that measure to extraordinary precision. And there is still a mass the size of 5 Hawaiis sitting in its mantle that we cannot explain. There is still a magnetic record that fluctuated when it should have declined. There is still a chemical asymmetry so profound that one hemisphere looks geologically ancient and the other looks geologically active by comparison, and the mechanism that produced that asymmetry is still, despite everything, not fully confirmed. This is what the science looks like right now, not at the threshold of resolution, but at the threshold of understanding the question clearly enough to resolve it. The last 2 years have sharpened the question. The next 5 years may answer it. What we do not yet know is how all these pieces fit into a single coherent model of lunar evolution. Every proposed mechanism that explains one asymmetry creates complications for another. The thermal explanation for crustal thickness does not fully account for the K-R-E-E-P distribution. The impact redistribution model for creep does not cleanly explain the water asymmetry. The deep interior models that might account for the buried mass create challenges for the magnetic evolution story. The puzzle pieces exist. They are sharp-edged and real. They do not yet fit together neatly. This is where the next phase of exploration comes in. The Artemis II mission will land on the Moon's south pole. For the first time since Apollo 17 in December 1972, a human being will step onto the lunar surface. And this time, the landing site has been chosen partly based on geochemical models that predict it sits directly on top of SPA ejector material. The astronauts who land there will be collecting the geochemical evidence that can test whether the SPA impact is truly the cause of the Moon's asymmetry, or whether something else was at work. China's Chang'e 7 mission is targeting the lunar south pole as well, with instruments designed to probe permanently shadowed craters for water ice, to characterize its chemistry and concentration, and to search for organic compounds that may have been delivered to the Moon by cometary impacts over billions of years. Future missions are being designed to carry seismometers back to the Moon, to probe its internal structure by measuring how seismic waves pass through it. The Apollo missions placed seismometers on the near side and generated decades of data. We have no seismic data from the far side. The structure of the far side crust and mantle, the depth and nature of the mantle crust boundary, the size and state of the core are still inferred from gravity data rather than measured directly. There is also the question of the radio telescope. The far side of the Moon is, from an astronomical perspective, the quietest place within easy reach of a human spacecraft. Earth's ionosphere blocks radio waves from space in certain wavelength ranges, and Earth's own radio emissions fill the sky with noise that makes some observations impossible from Earth's surface. The Moon shields its far side from all of this. A radio telescope on the far side would be able to observe wavelengths of radio emission that are completely inaccessible from anywhere on or near Earth. Among the targets for such a telescope would be the radio signature of neutral hydrogen in the very early universe, the so-called cosmic dark ages, before the first stars formed. This signal, if it could be detected, would be a direct observational window into the first few 100 million years after the Big Bang, before the universe became transparent to light, when the only structures in existence were the first clouds of hydrogen slowly pulling together under gravity. The Moon's far side, which the Artemis II crew have just seen and confirmed and photographed, is the platform from which that window might be opened. One object, two different sides. One face we have known for centuries. One face we have known since 1959 in photographs, and since this week in direct human observation. And behind the second face, if the telescopes are ever built, the earliest light in the universe. The crew of Artemis II are on their way home. They left the Moon behind at high speed, falling back toward Earth on the same free return trajectory that physics inscribed in their path days ago. The distance to Earth is shrinking by thousands of miles per hour. By Friday, April 10th, they will be in the Pacific Ocean, off the coast of San Diego, fished out of the water by the USS John P. Murtha, completing the first crewed lunar mission since 1972 and the farthest crewed journey in the history of human spaceflight. 252,756 miles from Earth, more than 4,100 miles farther than the previous record, held by the Apollo 13 crew in their emergency return in 1970. The record matters less than what was seen along the way. For 7 hours, 4 human beings looked at a geological object that has never been directly seen before. They described it in terms that will inform the next mission's landing site selection, the next round of sample analysis, the next generation of models about how rocky planets form and evolve. They saw the craters and the brightness and the jagged terminator and the enormous wounds and the ancient highlands, and they reported back in real time. and the scientists on the ground added those observations to a growing body of evidence. The moon is two different objects in one sphere. One of them faces us, and we have studied it for centuries. The other has been invisible to the human eye for all of human history, hidden behind its own near face, knowable only through instruments until now. What those instruments have found, what the samples have confirmed, and what human eyes have now directly verified, is that the hidden side carries a record of the moon's most violent and formative event. An impact 4.25 billion years ago that restructured the interior, redistributed the chemistry, set the two hemispheres on different evolutionary paths, and left a scar large enough to swallow continents. That scar is now confirmed up close by human observers. Its edges have been described and photographed and named. The investigation is not complete. It may not be complete in any of our lifetimes, but it is accelerating in a way that it has not accelerated since the Apollo era, fueled by the first farside samples, by the precision gravity maps, by the magnetic records frozen in ancient basalt, by the orbital imagery from a dozen different missions, and now by the observations of 4 human beings who went to a place no human had ever gone and came back to tell us what they saw. The far side is not dark. It receives as much sunlight as the near side. What it lacks is a view of Earth. From the far side, Earth is not in the sky. It has slipped below the horizon. You are in a place from which home is invisible. 4 people watched Earth disappear behind the lunar limb this week. They watched it set and they called the photograph Earthset, and the image is a version of the famous Earthrise, but reversed. Not a home appearing, a home going away, and in the time it takes to look at that photograph, the moon continues to turn in its ancient locked orbit, the same face toward us and the same face away, holding its secrets in a crust that is 60 kilometers thick in places, in a mantle that is 100 degrees colder than the side we know, in basalts that formed 2.8 billion years ago from an ultra-depleted interior that should not have been hot enough to erupt, but somehow was. The data is incomplete. The models are contested. The buried mass has no confirmed explanation. The magnetic rebound has no confirmed cause. The mechanism for the creep asymmetry is still being debated after 6 decades of lunar science. But the instruments are getting better. The samples are more diverse. The missions are more capable. And for the first time since 1972, human beings are going back. Not just to look, but to pick up the rocks and bring them home and find out what they say. The moon has been above us for 4.5 billion years. We have been looking at it for perhaps 300,000 years of human history. We have been measuring it with instruments for about 65 years. We have been walking on it, briefly, for 12 years of that. And in the last 2 years, we have learned more about what it actually is, about its interior, and its history, and its asymmetry, and its relationship to the early solar system, than in all the years before. The investigation is ongoing. We are the species doing it. And now, for the first time, we have been to the other side, and we have seen what is there, and we can confirm it is stranger than we knew.